Hello students, welcome to MEMONEET. This is Ravikant, the physics teacher, and today here we are to study magnetism. In this is the third video for your BPT 8. I hope you all have attempted BPT 7, right? BTS 7, and you have checked your answer key and you have found out how you are scoring and how well you are doing in all the subjects, right? Now in your BTS 7, after scoring it, please post your doubts in the group and that would be resolved, and you can use your PYQ book also to solve the doubts. In the last two videos which we have seen about the Biot-Savart's law, Ampere circuit law, we have seen about the solenoids, we have seen how the force has been exerted on a moving charge in a uniform magnetic field. We also saw how the force has been exerted on current carrying conductor using Fleming's left hand rule. We also saw about Maxwell's right hand thumb rule, right? We saw the moving coil galvanometer and how the galvanometer can be converted into an ammeter and a voltmeter. All these things we saw in the last two videos, and I hope you have gone through the videos. And if you have not gone through the video, please go through the video, see the video, and if you have any doubt, if you have any problem, please drop your doubts in the comment box there, and we will try to reply. We will definitely reply. We will definitely reply for your doubts in the comments over there. And please go through the video once and then solve the numerical and practice. We always say that once you are gone studied the concept, you should practice the numericals for that particular concept. Then only it will result in a better manner for you. The understanding will be better. So beginning with the magnetism. In magnetism we are going to study about bar magnet first. So bar magnet is basically your magnet which is in the form of bar, right? So if it is in the form of bar, it's a rectangular bar, right? Its two ends are known as the pole of the magnet. One of the end is marked as north, another end is marked as south, right? So this is a bar magnet, and this bar magnet has some properties. First property is that it attracts metals or materials like iron, cobalt, nickel, right? And it attracts most of its particles at the poles and less particles away from the pole. That is, the pole strength or the magnetic strength is more at the poles and is less away from the pole, whether it is a north pole or a south, right? And if we suspend this we suspend this bar magnet with the help of a string, and it is free to rotate about this string, then what we find that this bar magnet aligning itself along the geographical north-south. That is, the north of the bar magnet will point towards the geographical north, and the south of the bar magnet will point towards the geographical south. Third property is that if I break this magnet into two parts or more than two parts, every part will have a north pole and a south, right? That is, this magnet will always have both the poles in its every part, right? It's not possible that if there is a magnet with you, suppose this is a magnet, right? And here it is north and here it is south, and you break this magnet from here, then it would be only north and only south. This is not possible. This is not possible. If you are breaking a magnet into two parts will always, or each part will always have both the poles in it. That if we are breaking the magnet into two parts, then one of every part will have north pole and a south, right? North pole and a south pole. That is, both the poles are always present in every part, right? Now for a bar magnet, there are few basic things you should know, right? Because these are terms which they use in the numericals or in the questions. If this is north and this is south, then the line passing to the center of the bar magnet, this is known as the magnetic axis. This is known as magnetic axis. And If I draw a line which is a perpendicular bisector of this, then this is known as magnetic equator, right? This is known as magnetic equator. Now the length between the poles is known as magnetic length, and this magnetic length is less than the physical length of the magnet, right? A bit less than, but it is smaller than the physical length of the magnet, right? So we can consider this bar magnet. Consider this bar magnet. Suppose this is north, this is south. We can consider this similar to a dipole we studied in electrostat. This is plus q and this is minus q, separated by a short distance 2L. Right? So we call this as electric dipole. Right? We call this as electric dipole, and this will be called as a magnetic. We call as magnetic dipole. Right? So magnetic dipole, and if it is a magnetic dipole, it will have magnetic moment. So the field strength of the pole is being given by Qm. Right? Is being given by Qm. If this pole is having a field strength of Qm, this pole will also have a field strength of Qm, right? So the magnetic moment of this magnet will be given as for this we will give P vector is equals to 2QL, or you can say it we write this Q into 2L. In the same manner, here the magnetic dipole moment is given by M vector, and this is equals to Qm into 2L. This is magnetic dipole moment. This is magnetic dipole moment, right? Now, moving forward, the way we calculated the electric field intensity will always be taking reference of the electrostatics, because it is very easy to understand magnetism with the help of electrostatics, which we have already studied. What we have studied in electrostats is that suppose if we are having a dipole in which this is Q and this is minus Q, this is minus Q, and the length is 2L. In this case, any point lying on this line was known as axis of the dipole, and any point lying on this point was known as, if this was point P, this position was known as end-on position, and this was known as axis of the dipole, and the line perpendicular bisector of the dipole. Any point lying at this point was known as broadside on position, and this line is known as equatorial, right? And for both the position, for the broadside on position and for the end on position, we calculated the electric field intensity, and the electric field intensity for axis was, if you remember, 1 by 4 pi epsilon naught 2p upon r cube, where r was the distance of the point P from the center of the dipole, right? Similarly, electric field intensity at the equatorial line was equals to 1 by 4 pi epsilon naught P upon R cube, right? P upon R cube. So, similarly, if we are considering a bar magnet as a magnetic dipole, here it is north and here it is south, then if this is the axis of the magnet, this is the axis of the magnet, and we have a point P over here at a distance r from the center of the magnet, right? Center of the magnet, then the magnetic field intensity B vector B will be equals to mu naught upon 4 pi 2m upon r cube, right? 2m upon r. And if we need to know the direction, so I'll write this in the vector form. Then b vector will be equals to mu naught upon 4 pi 2 m vector upon r cube. So this expression tells you that the direction of the magnetic field intensity at point P will be in the direction of the magnetic moment. Now the question arises, what is the direction of magnetic moment? So magnetic moment is always in the direction of the magnetic field, that is, it's from north to south. This is the direction of magnetic moment, right? And if this is the direction of magnetic moment, this is if this is the direction of magnetic moment, then the magnetic field intensity at this point will be having direction in this direction. That is, this will be the b vector at this point, right? This will be the b vector at this point. So the direction of this b vector, that is magnetic field intensity vector, will be in the direction of magnetic moment, right? Now this is on the axial point. Now if we see this for equatorial line, this is the bar magnet, this is north, this is south, and this is the equatorial line, and this is the point P, which is at a distance of r from the center of the center of this bar magnet. Then the magnetic field intensity at P is given as B is equals to mu naught upon 4 pi m upon r cube. And if I write it in the vector form to mention the direction, then B vector will be equals to minus mu naught upon 4 pi m vector upon r cube. What does it mean? That the magnetic field intensity at point P will be in a direction opposite the direction of the magnetic field. So this will be the magnetic moment. So this will be the direction of the magnetic field at point P, and the direction of magnetic moment is in this direction. This is the direction of magnetic moment M, right? So for the equatorial line, the magnetic field intensity will have its direction opposite the direction of the magnetic dipole moment, right? Magnetic dipole moment. So what we saw is that for E axial, we had 1 by 4 pi epsilon naught q, epsilon naught 2p upon r cube. Then for V at axis, we had mu naught upon 4 pi 2m upon r cube. So if we see this, it will be easy for us to remember, right? And the derivation is exactly same as we did in the electrostats, right? So the derivation is not that required or not that important over here. So I'm not getting into it. But derivation is exactly same as we did in the electrostats. And similarly for your equatorial line, that is E at equatorial line is equals to 1 by 4 pi epsilon naught P upon R cube. So here B at equatorial line is equals to mu naught upon 4 pi m upon R. So what we see is 1 by 4 pi epsilon naught is being replaced by mu naught upon 4 pi, and your P is being replaced by M, right? Just everything is as it is. So this will be easy for us to remember, right? This will be easy for us to remember. So just to, understand it well, let's see one numerical over here. and the numerical says that two two identical magnetic dipoles of magnetic moment 1 ampere meter square each are placed at a separation of 2 meter with their axes perpendicular to each other. What is the resultant magnetic field at a point midway between the dipoles? So they are saying that there are two magnets and the magnetic moment for the magnets are being given to us, and they are saying that they are placed in such a manner that their centers are separated by a distance of 2 meters, and their magnetic moment is perpendicular to each other, right? So we can say that if suppose this is one magnet, let this be north, and this is south, then the another magnet has to be like this, right? So this is north and this is south, and the separation between them is 2 meters, and we have to find what is the resultant magnetic field at the point midway. We have to find the resultant magnetic field at this point. It means from this magnet this distance will be taken as 1 meter, and from this magnet it will be taken as 1 meter. So let this be the magnet 1 and let this be the magnet 2, right? Magnet 1 and magnet 2. Now for magnet 1, we can see that point P means point at which we are supposed to calculate the magnetic field is, we will write it as B1, and this point P is at the what axial line, that is axis. So magnetic field B1 will be equals to mu naught upon 4 pi into 2m upon r cube, right? And similarly, B2 will be for the second magnet, point P is at the equatorial line. So for equatorial line, we will have magnetic field as mu naught upon 4 pi m upon r cube, right? So putting the values here, will get 10 to the power of minus 7 into 2 into m is 1 for both the magnets upon r cube. R cube is again 1. So from here we'll get 2 into 10 to the power of minus 7, and this will have its magnitude as 10 to the power of minus 7 into 1 into 1 upon 1. So this will be equals to 1 into 10 to the power of minus 7. So at point P, if I draw it here, point P, this would be the direction, sorry, this would be the direction of magnetic field V1, and this would be the direction of magnetic field V2, right? Because V2 is supposed to be in the direction opposite the direction of magnetic moment. So here the magnetic moment will be in this direction, and here the magnetic moment will be in this direction, right? So magnetic field will be in this way, and this is the point P. This is the point P, and the angle between these two will be equals to 90 degree. So the resultant will be given as, using our concept of vector, we will say that B is equals to under root of B1 square plus B2 square. Putting the values, you will get B is equals to root 5, right? Root 5 into 10 to the power of into 10 to the power of minus 7 Tesla, right? This will be the resultant magnetic field, magnitude of the resultant magnetic field. So your resultant magnetic field will be somewhere here, completing the parallelogram. This will be the resultant magnetic field, and if it is making an angle theta with B1, Then we will say tan theta is equals to B2 upon B1, right? And theta will be equals to B2 upon B1. So we'll get tan theta is equals to 1 by 2, which is equals to 0.5. For this, theta will be equals to 26.57 degrees, right? So this is the direction of the magnetic field, resultant magnetic field at point P, right? So simply this is calculating this value is formula based, and the direction and the resultant magnitude is your concept of vectors. So I always tell that you should study well your vectors in your 11th standard, because it will be applied in more extent in your 12th standard in your electrostats and magnets, right? So if you understood this numerical, let's move forward with our topic. So this was how a bar magnet was similar to an electric dipole, and we consider this bar magnet as a magnetic dipole having different poles at two different ends. So if we are considering a bar magnet as an electric dipole, and we are means treating it similar to the electric dipole, but the variables and the proportionality constant has changed. So we will treat it further similarly. If you remember that for a uniform electric field, why I'm always talking about the electric field? Because if you remember electrostats well, it will be very easy for you to understand magnetism. A dipole was being placed in it, was minus q, this was q, and the dipole moment will be in this direction. This will be the dipole moment. The angle was theta. So in this case, the torque was being given as tau is equals to P E sine theta, right? P E sine theta, or we wrote tau is equals to P vector cross E vector, right? Similarly, if in a uniform magnetic field, this is a uniform magnetic field, the way we represent an uniform electric field by parallel and equidistant line, the same way we will represent the magnetic field with parallel and equidistant line, and there is a bar magnet being placed in it. That is, suppose this is south and this is north. It will have its dipole moment in this direction, let's say m, and this makes an angle theta. This is the magnetic field B vector. Then the torque experienced by this bar magnet will be given as tau is equals to m b sine theta, or we can say that tau is equals to m vector cross b vector, right? M vector cross b vector. Again, I would repeat that the derivation for this formula is not important here, because the derivation is similar to the derivation we did in the electrostats. If you remember it, in the same way we can derive these formulae, and derivation is not relevant over here because we just need the formula, right? So just remembering the formula will do. So if the angle between, again the same analysis as we did here, if angle theta is equals to 0 degree, it means the bar magnet is being placed or aligned parallel to the or in the along the magnetic field, then the torque will be equals to 0, right? For theta is equals to 90 degree, that is, a bar magnet is being aligned perpendicular to the magnetic field, that is, this is the magnetic moment. In this case, your tau will be equals to maximum, that is m into b, right? M into b. So this is torque. This is the torque. Now similarly, as we studied in our electrostats, the potential energy in a system in which uh, Dipole is placed in a uniform magnetic field. Dipole is sorry, in a uniform electric field. In that case, we had U is equals to minus PE cos theta. So similarly, here in magnetism, we will have potential energy will be equals to minus MB cos theta. Why again I'm taking electrostatics and magnetism all together, because both are treated similarly. If you have understood electrostats very well, it will be easy for you to understand magnetism, right? So, and if you do not, if you have not understood electrostats very well, go and study it, and if still you do not feel like studying it, just remember the formula, that is U is equals to minus B cos theta. But I would suggest go and study electrostats. It's very easy to understand electrostatics as comparison to magnetism. And once you have understood electrostats, in the same sense we can understand magnetism. Why it is so? Because both of the things, that is the electrostatics and the magnetism, are related to the vector field, and both are of non-contact forces, right? So everything is treated in the similar manner. Only the parameters changes. That is, instead of using the permittivity, we use permeability. That is, instead of using epsilon naught, we use mu naught. We write there in the electrostatic, we write 1 by 4 pi epsilon naught. Here we write mu naught upon 4 pi, right? There we write magnetic dipole. There we write dipole moment as P. Here we write the dipole moment as M. There we write electric field intensity as E. Here we write as magnetic field intensity as B. The sense of understanding the things are same, because both are vector fields and both are to be treated similarly, right? So if the potential energy there in the electrostats was U is equals to minus PE cos theta, here in the magnetism it will be equals to minus MB cos theta, right? Minus MB cos theta, or you can say that U is equals to minus M vector dot B, M vector dot D B vector, right? Now we will see that a current carrying loop is also will also behave as a pure magnetic dipole. Now, suppose this is a loop, and here I connect it with a battery. Right? If I'm connected it with a battery, the current will flow in this direction. Right? It will flow in this direction. I've already discussed in the last video also. Now, if the current is flowing in this direction, if we need to find the direction of the magnetic field in this, we use Maxwell's right hand thumb rule. Now, if I hold the wire in my hand using the right hand Maxwell's thumb rule, my thumb is indicating in the direction of the current, right? Is indicating the direction of the current, and my fingers are getting into the loop, right? If I hold, my fingers are getting into the loop. Therefore, the will be magnetic field will be getting into the loop, getting into the loop, right? And we know that for a bar magnet, if this is north and this is south, magnetic field originates from the north pole and terminates in the south pole, right? This is how the magnetic field is: originates from north, terminates in south. And if this is the case, it means the end of a magnet in where the magnetic fields are entering, here the magnetic field is entering into it, that would be a south pole, and the point from where the magnetic fields are exiting, that will be a north pole, right? So here what we find, that in this loop, when the current is going in the clockwise direction, the magnetic fields are entering, getting into the plane where I have drawn the loop, right? The fields are getting into it. So this will be nothing but the south pole. Now if in a loop the current is flowing in a clockwise direction, if this is the clockwise direction, if you see it from behind, if you see it from the other side, if you see it from the other side, it will appear anti-clockwise. It will appear anti-clockwise. And if the current in the loop is flowing in the anti-clockwise direction, suppose this is the loop, right? And this is the case. then the current will flow in the anti-clockwise direction. Again, use the Maxwell's right hand thumb rule, holding the loop. My fingers will come out of the loop here, like this, right? It won't get inside it. It will always come outside. If I hold the loop, current is in the anti-clockwise direction. My fingers will come out of the loop. So the magnetic field are coming out of the loop. And if it is coming out of the loop, this will behave as a north. So same loop carrying current in one of the direction. From one side it will behave as a north pole, from the other side it will behave as a south pole. So a current carrying loop itself behaves as a magnetic dipole, right? This is what I wanted to make you all understand, that a current carrying loop also behaves like a magnetic dipole. And if the current flowing in the loop, we consider it as I, and the area enclosed by the loop is A, then the magnetic dipole moment M is given as I into A, and magnetic dipole moment being in a vector quantity, we write it like this, then here we write it like this. It means that the magnetic dipole moment is in the direction of the area vector, right? Is in the direction of the area vector. It is definitely in the direction of the north pole, right? Means it moves out of the north. So this is your current loop as a magnetic dipole, right? So it will have its magnetic dipole moment as M is equals to I into A. M into I into A. So again, related to this, we have some numericals. Let's see the numerical. The numerical says that a planar loop of irregular shape. The shape is irregular, but encloses an area of 7.5 into 10 to the power of minus 4, 10 to the power of minus 4 meter square, and carries a current of 12 ampere. Okay, the sense of flow of current appears to be in the clockwise clockwise at an observer. Now, what is the magnitude and direction of the magnetic movement vector associated with the current loop? So it is easy. It's directly formula based. They are asking you the value of M. So M is equals to I into A. First, we are calculating the magnitude. So M will be equals to I. They have given to us is your 12 ampere, and A is being given to us is 7.5 into 10 to the power of minus 4 meter square. Multiplying this will get our dipole moment as 9 into 10 to the power of 9 into 10 to the power of minus 3 minus 3 ampere meter square, right? Ampere meter square. Now they are saying that the current is flowing in the clockwise direction. So if it is flowing in the clockwise direction, this is the direction, then the magnetic field will be entering into the loop, right? And this is south pole. So magnetic dipole moment will be perpendicular to the page and it will be acting inward. So this will be the direction. This will be the direction of the magnetic moment. M will be in the direction perpendicular to the page and getting into the page plane, right? So this is the magnitude and direction of the magnetic moment vector associated with this current. Now next it says a bar magnet of dipole moment 3 ampere meter square rests with its center on a frictionless pivot. A force F is applied to a right angle to the axis of the magnet 10 centimeter from the pivot. It is observed that an external magnetic field of 0.25 Tesla is required to hold the magnet in equilibrium at an angle of 30 degree with the field. Calculate the value of F. Okay. So what they are saying is that there is a bar magnet, right? There's a bar magnet being placed on a pivot, right? This is the center, and let's say this is south and this is north, then a force is being acting perpendicular to the or at 90 degree, and this distance is given as how much, 10 centimeters, right? And this torque is turning it to an angle of, this magnet turns to an angle of 30 degree, and to keep this in equilibrium, that this force may not turn it further, there is another torque applied by an externally applied magnetic field, and then that torque is balancing the torque by this force, right? And the magnet is in equilibrium at an angle of 30 degrees. This is what they are telling. So if it is in equilibrium, it means the torque applied by the external force, I write it as Ex, is equals to torque applied by the magnetic field, right? The torque applied with the external force will be F into R, the distance between the action of line and the fixed point. So that has been given as 10 centimeters over here, and the torque applied by the magnetic field is given as mb sin theta, right? So tau is equals to mb sin theta, right? Tau is equals to mb sin theta. So we will write this as f, which we need to find, and r is 10 into 10 to the power of minus 2 converted into meter. Magnetic dipole moment is given as 3 ampere meter square into external magnetic field is being given to us as 0.25 Tesla, 0.25 Tesla into sine theta. Theta is 30 degrees, so sine 30 is equals to 1 by 2. 1 by 2. So from here we'll get, after calculation, we'll get F is equals to 3.75 Newton. 3.75 Newton. You can simply calculate it and we'll get the answer as 3.75 Newton. So this is the force which has been applied externally to keep this magnetic dipole or a bar magnet in equilibrium in the external magnetic field, which is of 0.25 Tesla, right? So now again moving further, what we have to see is, yep. So what we have to see is your solenoid is equivalent, a bar magnet is an equivalent to solenoid, means a solenoid and bar magnet are equivalent to each other. See, what is a bar magnet? See, this is a bar magnet, right? What this bar magnet has? It has a north pole and a south pole. Magnetic fields running like this from north to south, from north to south, north to south, and from north to south, right? This is the direction of the magnetic field. Now, if I draw a solenoid, right? Now, how solenoid is drawn? Yes. Please bear with my drawing skills. I'm very poor in it. Just trying to give the actual representation, but I'm very poor in my drawings. So just bear with me. If I make this as a positive terminal and this as the negative terminal, what will happen? The current is moving in this direction. From below it is coming and then it is going like this. Then again it is going like this, going like this, going like this, and then going like this. So if you see from here, what you find, just try to visualize the thing that the current is going in this direction, right? So this is a clockwise direction. So if the current is flowing in this loop as in a clockwise direction, what pole will be generated over here? It will behave as a south pole. Now if you look from this side, the current is flowing in this direction, right? That is from up, it will be going down. From up, see, from this here, from here, the current is going like this, from here down, and from down it's coming up and then like this. So if you look from this side now, this current will appear to go in this direction, that is anti-clockwise. And when it is anti-clockwise, a north pole will be developed from here. And let me make you understand in another way also. See here the current in this in this wire, you see the current is in downward direction. So using Maxwell's right hand thumb rule, current is in downward direction. So the magnetic field will be entering into this end, right? Coming to this end, again the current is in downward direction. Using the Maxwell's right hand thumb rule, the magnetic field will be exiting this end. So if the magnetic field are exiting this end, this will be north pole, and if it is entering into this end, this will be south pole. So the solenoid is also nothing but a bar magnet having two poles in it, south and north pole, right? So this is how this solenoid will also behave as a bar magnet. Inside the solenoid, the magnetic field will be from south to north. Inside the solenoid, the magnetic field will be from south to north. So your solenoid will also behave as a bar magnet. Now some analogy from your electrostats. We have Gauss theorem over there, right? We had Gauss theorem over there. What was Gauss theorem? Gauss theorem says that closed integral E dot dA is equals to E dot ds. E dot ds or E dot dA is equals to Q upon epsilon naught, right? That is the surface area. Here we have closed integral V dot ds is equals to mu naught into I is equals to mu naught into I, and this is nothing but what? The Ampere circuital law, right? The Ampere circuital law. So for a dipole in an electric field, what we saw that if this is the Gaussian surface and we are having a dipole in it, minus q and plus q, right? So the net charge enclosed is equals to 0. So the electric flux passing through the surface was also equals to 0. Phi E was equals to 0. In the similar manner, if in a loop, closed loop, there is a let's say a magnetic dipole. Let's say it's a magnetic dipole. Here we have north and here we have south. Then the magnetic flux passing through this phi b will be equals to 0, right? Phi b will be equals to 0. So similar to the Gauss theorem which we have studied there, the Gauss theorem in the magnetism also we have, right? So ending up with this, now the next thing which we have to study is the magnetic materials. Before that, we have to study some important terms used in the magnetic properties of the material, right? The next thing which you have to study is the magnetic property of the materials. We have three types of material, that is paramagnetic, diamagnetic and ferromagnetic materials, right? So that you must have studied very well in your what in your chemistry. So first we see some terms. The terms which we are going to see is, the very first term is your magnetizing field. It is magnetizing field, right? So from here, what I want you all not to note down something, but I want you all to understand it. What magnetizing field, according to definition, is, it says that the magnetic field that exists in vacuum and induced magnetism is called magnetizing field. That is, if there is an external field present and there is a substance in which we need to induce magnetism, then this external field is known as magnetizing field. Means that field which is inducing magnetism in some another substance is known as magnetizing field, right? Now the next thing which we need to understand is magnetic induction. Your magnetic induction. Magnetic induction means the magnetic property which got induced in this substance because of this magnetizing field. So what magnetic induction is defined as, the total magnetic field inside a magnetic material is the sum of the external magnetizing field and the additional magnetic field produced due to the magnetization of the material is called the magnetic induction. Means all over the magnetization which happened into the material because of the external field and because of its own magnetizing property. Whatever is the magnetic property induced in the substance is known as its magnetic induction. Right. Now next is your magnetizing field intensity. This your magnetic induction is being given by B, right? It has been given by B, and suppose we are talking about a solenoid, so it will be B will be equals to mu naught N into I, right? For a mu naught solenoid, it will be equals to mu naught into N into I. Now we have magnetizing field intensity. Magnetizing field was the external field which was used to magnetize the substance. So intensity means to what extent it has been imposed at a particular point. So magnetizing field intensity, it is being given by H, and H is equals to N into I. So you can say that B is equals to, or B naught is equals to, we have mu naught N into I. So we will have B naught is equals to mu naught into H, or you can from here say that H is equals to B naught upon mu naught, right? That is magnetizing field intensity. That is magnetizing field intensity. Then intensity of magnetization. Next thing is your intensity of magnetization. Intensity of magnetization, magnetization, right? Intensity of magnetization, that is the magnetic moment developed per unit volume. Magnetic moment developed per unit volume of a material when placed in a magnetizing field is called intensity of magnetization, or simply magnetization, right? So intensity of magnetization, you see what we are doing is we are having an external field which is used to magnetize the substance. So this external magnetic field is known as magnetizing field. Now, when this substance is magnetized, the magnetic property induced or developed in that material is known as magnetic induction, right? And then we have the magnetizing intensity, the intensity of the field which is used for magnetizing the external magnetic field which is used for magnetizing. The intensity of that particular field is known as magnetizing intensity. Then intensity of magnetization means the intensity at which the substance is got magnetized. The substance which is magnetized is known as the intensity of magnetization. Again, the intensity of magnetization is the intensity to which the substance is got magnetized. So we define it as the amount of magnetic dipole moment the uh, developed per unit volume in that particular substance which was kept in an external magnetic field to get magnetized, right? That is, suppose we are having an external magnetic field and we are placing a cobalt in it, or we are placing an iron bar in it, and we are applying that external magnetic field on it. Now, that iron bar will attain some magnetic field, magnetic properties, right? Then, if it is attaining as a magnetic property, it will have some north pole and south pole, and then definitely it will be having magnetic dipole moment, and that magnetic dipole moment divided by the volume of the bar which we use, that will give you the intensity of magnetization. So intensity of magnetization is being given by capital M vector, and this is equals to small m vector, that is magnetic dipole moment per unit volume of the substance, right? Per unit volume of the substance. So we have one more relation with it is your B is equals to mu naught into H plus M. B is equals to mu naught into H plus M. So what you are supposed to do is you are supposed to remember the formulae, the expressions which I have written in the box. That is B is equals to mu naught into H plus M. H is equals to B naught upon mu naught, and thus we know that B is equals to mu naught into I. Then again we have relative permittivity. right? Relative permittivity is what? Mu r, and mu r will be as relative permittivity we have studied in electrostats. Here we have relative permeability. Relative permeability will be equals to mu r, and mu r will be equals to mu upon mu naught. As we had epsilon r, we had epsilon r is equals to epsilon upon epsilon naught, right? In the same manner, we have mu r is equals to mu into mu naught, right? Then we have magnetic accessibility. Magnetic accessibility. Magnetic magnetic accessibility is represented by Xi, and Xi is written like this, and this Xi is given as capital M upon H, right? This Xi is given as capital M upon H. That is the ratio of the magnetization upon magnetizing intensity is known as Xi, right? This is the magnetic dipole moment W per unit volume, and this is the intensity of the external magnetic field which is used for magnetization. Ratio of these two will give you Xi, which is known as magnetic accessibility, right? Then relation between magnetic permeability and magnetic accessibility is, you again have to just simply remember it is, see, we have B is equals to mu naught into H plus M, right? So B will be equals to mu naught into H into 1 plus M upon H, and then we will have B is equals to mu naught into H into 1 plus Xi, right? 1 plus Xi. Yes. Then from here we have one more relation, that magnetic permeability is equals to B upon H. So B upon H, here we can write it as mu is equals to mu naught into 1 plus Xi. So this, when comes here, will be mu upon mu naught is equals to 1 plus Xi, and this is what? 1 upon mu r. 1 upon mu r is equals to, no, it's mu, sorry, it's mu r. Mu r is equals to 1 plus Xi, right? Now again I would say that all these derivations are not important. The only thing you are supposed to do is you keep this in your account. Remember the formula, that is intensity of magnetization M is equals to M upon V. Mu, that is permeability, is equals to V upon H. V is the magnetizing intensity, and this is magnetization intensity. Mu R is relative permeability, that is mu upon mu naught. Accessibility is M upon H. Accessibility is also C upon T. We will see what Curie's law is. Then B is equals to mu naught into H plus M, and mu R is equals to 1 plus Xi M. If you remember these formulae, it will be sufficient enough for you to solve the numericals and solve the questions for it. Right? Now let's come to Curie law. What Curie law says, that from experiment it is found that the intensity of magnetization means capital M, intensity of magnetization of a permanent magnet is directly proportional to the magnetizing field intensity, is directly proportional to magnetizing field intensity, that is H, and is inversely proportional to the absolute temperature, that is M is inversely proportional to the absolute temperature, that is 1 upon T. So combining this will get M is proportional to H upon T. This is what is Curie's law states. The Curie law, to remove the what proportionality, we'll write it as M is equals to C into H upon T, where the C is the proportionality constant and C is known as Curie's constant, right? Curie constant. Now from here, I would write it as M upon H is equals to C upon P, and the C M upon H we know is known as magnetic susceptibility. So write as magnetic susceptibility is equal to C upon P, right? So Curie's law say that the magnetizing intensity is directly proportional to the magnetization is directly proportional to the magnetizing intensity, and this magnetization is inversely proportional to the temperature. More is the temperature, less will be the magnetization, right? This what is the Curie's law. Now the next thing which we have to study without wasting a lot of time on it, what I will tell you is, see, these are the properties of diamagnetic substances, paramagnetic substances, and ferromagnetic, right? If you remember this table, or if you remember these properties, or a comparison of these properties very well, it will be very easy for you to answer the questions which are in the form of assertions and region, or if directly objective type questions. It will be very easy for you to understand. Let's see what they have written in it. Is summarize this table is basically the summary of all the properties of diamagnetic substances, paramagnetic substances, and ferromagnetic substances. It makes no sense in understanding a lot of things, because it is it is only that you have to memorize all the property to give your answers correctly, right? And you have already studied all these things in your chemistry also. So So the first property says the effect of magnets. That is when these diamagnetic substance, paramagnetic substance, or ferromagnetic substance are brought close to a magnet, the diamagnetic substance, they are feebly repelled by the magnet. Feebly means very to a very small extent. So the diamagnetic substances are feebly repelled by the magnets. Paramagnetic substance, they are feebly attracted by the magnets. Coming to ferromagnetic substances, they are strongly attracted. They are strongly attracted by the magnets. Similarly, in the external magnetic field, they acquire feeble, that is the diamagnetic substances acquire feeble magnetization in the opposite direction of the magnetizing field. So here they acquire a magnetization which is to a smaller extent, and it is in the opposite direction. Whereas the paramagnetic substance, they also acquire a very small amount of magnetization, and it is in the direction of the applied magnetic field. And coming to ferromagnetic substances, they acquire strong magnetization, and that too is in the direction of the magnetic field. In this way, you have to read all the properties. See here, they are talking about the accessibility. What is this accessibility? The accessibility of diamagnetic substances is lie between -1 and 0, whereas the flexibility of the paramagnetic substance is very small, that it lies between 0 and epsilon, where epsilon is a very small number. And then the accessibility of a ferromagnetic substance is very large, that is it is greater than 1000. So what we find is that the diamagnetic substances have a negative and a very small accessibility, whereas paramagnetic substances have a very small and positive accessibility, and the ferromagnetic substances have positive and very high accessibility, right? So this is how which you have to remember it. The thing is that you have to memorize all these properties and all these relationships. And once you remember all these relationships, it will be easy for you to answer the question. So if you want this property, this summarized table from my side, and you want me to share it, comment it in the comment box that you want this summarized table of all the properties, so that you can take a printout of it. I'll provide you the PDF of this, and you can take a printout of it, paste it in front of your study table, so that whenever you go through pass through your study table, you sit studying, you are getting a sight of this, and getting a sight of this every day, it will be easy for you to understand, or it will be easy for you to remember all the properties and the comparison of these properties. If you want the PDF of this comparison, or the summarized table of the properties of these paramagnetic, and diamagnetic substances, comment me in the comment box. Drop your comments in the comment box. Ask for it. That you want this table of the properties of paramagnetic and diamagnetic substances. I will definitely provide it to you. Right. So I want the comments. A good number of comments in the comment box. Then I will definitely provide it to you. the last thing which we have to study from here is the hysteresis loop. Now coming to the hysteresis loop, we'll just try to understand it. Here we have two axes. On one y-axis we have B, and on x-axis we have H. H is the magnetizing intensity. That is it is the intensity of the externally applied magnetic field, right? And B is the magnetic induction intensity. That is to what extent the external, so the substance got magnetized. This is H is the magnetizing intensity, that is the intensity of the externally applied magnetic field, and B is the to what extent the substance which was placed in the external magnetic field got magnetized, right? So we start from the origin. At this origin there was no external magnetic field, and there was no magnetic property in the substance. As we increase the value of H, as we increase the value of H, you can see the value of B goes on increasing like this, right? It goes increasing like this. Now this is the value of H max. Beyond this, there will be no effect of magnetization in the substance. If you go on increasing H, that is the intensity of magnetization, there will be no magnetic induction in the substance. Now, if I go on reducing the intensity of the externally applied magnetic field, what will happen? The substance will start getting demagnetizing itself. It will demagnetize, and as soon as the H reaches to zero, the magnetic property or the magnetic magnetization induced in the substance will not come to zero. It will retain some magnetic property in it. This is the value which it retains into it, and this OB, this intercept is known as retentivity. This intercept is known as retentivity. That is, we first magnetized the substance, and then by reducing or reversing the magnetic field intensity, we are trying to demagnetize the substance. But what we find that while reducing the intensity, as soon as we reach at zero, the substance do not get completely demagnetized. It retains some magnetic property, and this is known as retentivity. Now to completely demagnetize this, that is at this point C, you can see that B is equals to 0, but at C, H has reached some negative value. That is, if I want the magnetic substance to demagnetize completely, I will have to apply some reversed magnetic field, external magnetic field to some extent, and then only the substance which I kept for magnetization will demagnetize completely, and the entire magnetic property will disappear from it. And this intercept is known as your coercivity. Coercivity. Now, just for your clarity, if I remove it, so your this this intercept is known as retentivity, and this intercept is known as coercivity. That is, OB is equals to retentivity, and OC is equals to coercivity. Right? Now, if I further keep on increasing the reverse externally applied magnetic field, the substance will get magnetized in the opposite direction. It means if initially the end which was magnetized as a north pole will now get magnetized as a south pole, and which was being magnetized as south pole will magnetize as a north, and it will get magnetized to a maximum extent. And as we had H max here, in the similar manner we have H max here. That is the maximum externally applied magnetic field which we can apply. Beyond it, there will be no magnetization. Then again, if I start reversing it and reducing it to zero, if I start reducing the magnetic field intensity, that is the intensity of the externally applied magnetic field, and I bring it to zero again. Now see, at H is equal to zero, where is B? B is here. Again, it retains some magnetization. Now again, to demagnetize it completely, to reach at this point, we need some extra magnetic field, this region, right? This region. So this is coercivity in the opposite direction, right? And then again, further increasing H, the substance will get magnetized to the same extent, right? So what we understand from here is that if suppose I'm applying an external magnetic field from my left to right, and I'm gradually increasing its intensity to a maximum extent, suppose the substance is kept in the magnetic field, it will get magnetized, and this side, we assume that this side gets south pole, and this side gets the north pole. Now, if I continuously start decreasing the intensity of the externally applied magnetic field and bring it to zero, it never happens that the substance placed in the external magnetic field get completely demagnetized. It retains the magnetic property even though the magnetic field, externally applied magnetic field, is zero now, right? And this property of retaining this magnetic property is known as retentivity. Now what I'm doing is, now the magnetic field is zero. Now gradually I'm increasing the intensity in the opposite direction. It means initially the magnetic field was from my left to right. Now the magnetic field will be from my right to left, and I'm increasing intensity in this direction, right? So it means I have reversed the direction of the externally applied magnetic field, that is the magnetizing field. Magnetizing field. Now when I'm increasing the intensity of magnetizing field in the reverse direction, what will happen? Now the magnetic substance which got magnetized to a certain extent, it will start demagnetizing, and after some intensity of externally applied magnetic field, it will get completely demagnetized, which is the point C in the hysteresis loop over here, right? This is which is the point C over here in the hysteresis loop, and that is known as coercivity. Coercivity means it the extra work which we had to do to completely demagnetize the magnet. Then again, if I increase the intensity in the reverse direction, that is from right to left, then the magnet will get again magnetized in the opposite direction. Initially, it was having south here and north here. Now it will get south here and north here, right? So that magnet will get magnetized in the reverse direction. Then again, if I start reducing the magnetic field, it will again reduce some magnetic property, but it will not completely get demagnetized, and that is the point E. Now to completely demagnetize it, I have to further increase the intensity in the reverse direction. Now again the magnetic field will be from my left to right, and in this process the substance will get completely demagnetized at point F. At point F in the loop, if you see, right? And then if further I keep on increasing the intensity in the direction of from my left to right, the magnet will again get magnetized. That is again the point which is A, which is marked as saturation. So this is what is your hysteresis loop. So in hysteresis loop, it's important to understand which point is the your retentivity. This is retentivity in one direction, and this is the retentivity in the other direction. This is coercivity in one direction, and this is the coercivity in the other direction, right? This is what is your hysteresis loop. So here I end up with what I have to teach you all. Now what I have to tell you is, first thing, if you want this table as a PDF so that you can take a print out of it and paste it in your room so that you can remember things, then you have to drop your comments in the comment box, right? Second thing is, you this if I talk about this particular topic or particular chapter, magnetism, in this most of the things is your memory base. The very first thing is the property of paramagnetic, diamagnetic, and ferromagnetic substances, for which I will be providing you the PDF. The second thing is, all the relations for the magnetic dipole is completely analogous to the relations which we have studied for an electric dipole, right? If you understood the analogy, it will be very easy for you to remember all the formula and the concept, because the concept or the sense of the dipole, electric dipole, is same as it is for magnetic dipole. Means all the both the dipoles, the magnetic dipole and the electric dipole, both have the same sense of understanding. If you have understood the electric dipole, it will be very easy for you to understand the magnetic dipole. I show you the analogy between the formula for both the cases, right? So it will help you to remember those things. To understand it better, go through the numericals, solve it, go through the video once, twice, rewind it, forward it, see it in the slower speed, see in the faster speed for your revisions, and then solve the numericals, solve more and more questions for this chapter. Why I'm saying more and more questions for this chapter? Because it is completely memory based. So you have to memorize a certain amount of things for this chapter, that is especially the properties. I tell you repeatedly that you have to remember the properties of paramagnetic, diamagnetic, and ferromagnetic substances, because most of the questions come from there only, right? Most of the questions come from the property of this magnetic substances. So please go through those properties, memorize those properties, and try to solve more and more questions, because solving more and more questions will help you to understand, help you to remember or memorize these properly, right? So that is all from my side. Please go through the videos, and if you have any suggestion, if you have any doubt, drop your comments in the box. And one more thing, please go and purchase this your PYQ NTA PYQ book, because that would also help to enhance your concept and question solving capabilities, because it is entirely based on your NTA strategy of making question papers, and it will help you to build up a good approach for solving your math, right? So I guess a lot of suggestions for you all. Go study well, work hard, go score well, and be very well prepared for your BTS 8. Write your BTS 8 examination, score well in it, and then give me your feedback, right? That is all from my side. Thank you.